Hello, my name is Minshen Zhu, and I'm glad to present our paper Exponential Lower Bounds for Locally Decodable and Correctable Codes for Insertions and Deletions. This is a joint work with Jeremiah Blocki, Kuan, Cheng, Elena Grigorescu, Xin Li, and Zheng. So what did we prove in this paper? Very informally speaking, we proved that codes with the following properties must be exponentially long. Property 1. The codes admit very efficient local decoding procedures. And property 2. The codes can withstand a constant fraction of instilled errors. Before getting into more details, I'll try to explain the words highlighted in red, namely codes, local decoding, and instilled errors. Let's start with error correcting codes. Let sigma be a finite set. An error correcting code over sigma is a mapping C which maps n-bit strings over sigma to n-bit strings over sigma. Here sigma is the alphabet, n the message length, m the code word length. Delta C is the distance of the code, which is a very important parameter. It's defined to be the minimal distance between cx1 and cx2 over all distinct pairs x1 and x2 in sigma to the m. Here the distance delta is defined to be the number of coordinates where x and y differ. This is also called the Hamming distance between string x and string y. More often we're going to use the normalized distance denoted by d of c, and it's just going to be delta over m. So it will be a number between 0 and 1. And rho, the information rate, is defined as the message length over the code word length. It's also going to be a number between 0 and 1. We say C is binary if sigma is the set of only two elements, 0 and 1. We say C is linear if sigma is a finite field and C is a linear transformation between the n-dimensional vector space over sigma and the m-dimensional vector space over sigma. Now let's turn to decoding. The purpose of error correcting codes is to correct errors, and that's achieved by the decoder. Essentially, a decoder for a code C is an algorithm which inverts the encoding algorithm as long as the input string y is not too corrupted. So as long as there are at most delta min corruptions, then the decoder should succeed. However, we're more interested in local decoding, which is the subject of this paper. So let's take a look at this diagram. We have some input message x, and then the message is encoded into a code word C, which is usually longer. And then the code word is sent through some adversarial channel and gets corrupted to some C tilde. And here's the local decoder. Note that it's only interested in one bit of the input message instead of the entire message as in the global decoder case. So what's the deal here? Well, the deal is that since we're only interested in one bit, we don't want to read the entire C tilde. Instead, we want to make as few queries as possible into the code word while still being able to decode xi correctly for all index I. So that's local decoding. And formally, we have the following definition. For locally decodable codes, we have three parameters: q, delta, and epsilon. So this delta here corresponds to the amount of errors the code can correct, and epsilon corresponds to the success rate of the decoder, and q corresponds to the number of queries the decoder makes into the received string. And note that here we're being lenient to the decoder since we only want a epsilon advantage over random guessing here. A central question in this field is the following. Given q delta epsilon, what is asymptotically the optimal m? So here we should think of m as a function in the message length n. Here's a simple example of LDC. It's called the hardmark code. So in short, the hardmark code is locally decodable using only 2 queries, and it has exponential length. And this is also optimal for locality 2. Okay, finally let's explain what are instill errors. So far we have been dealing with Hamming errors. So those are just bit flips. And instill stands for insertions and deletions. Insertions are errors of the following form, where one could insert bits into consecutive bits of the original string and produces a longer string. Deletions are errors of the following form. One could take out some bits of the original string and pushes the rest of the bits together to form a shorter string. This step in the middle is behind the scene, and we only get to see the final output. For these errors, we're going to use a different distance metric, the added distance. So the added distance between x and y is the minimal number of insertions and deletions to transform x to y. And it's not hard to see that the added distance between x and y is at most twice the Hamming distance between x and y. But it's not in the other way around, so we could have 2 strings with very small Hamming distance but with very large added distance. So in this sense, instill errors are much more difficult to handle than bit flips. Here's a brief history about Insta Codes. The study of Insta Codes dates back to Levenstein in the 60s, and we don't have any efficient constructions until the late 90s when Schurman and Zuckerman gave the first efficient construction. And so this is not a very exciting research field until 5 years ago, when synchronization strings are introduced, and since then there have been a lot of constructions based on synchronization strings. And for the local variant, namely instill LDCs, there have not been many works. There are only a few of them, and the first 3 are all constructions, and the last one, which is our current paper, is a lower bound. Okay. Now we're about to give a formal definition of instill LDCs, but before that, let's recall the definition of a Hamming LDC. So here's the formal definition, and we only need to change in a few places to obtain the definition of instill LDCs. So here's the definition, and probably the most noticeable change here is that the string y will have a different length m prime than the code word length m. This is because both insertions and deletions can potentially change the length of a string. And also here that we give the length of the received string as an input to the decoder. And we choose to do that because we're proving lower bounds for such codes. And giving this extra information to the decoder only makes our lower bound results stronger. Okay, so much about Insta LDCs. Here's a table of what has been known for Hamming LDCs. So we have all these upper and lower bounds. And all these bounds are divided into 3 regimes according to the query complexity. And in a constant query regime, we have 2 cases. When the query is exactly 2, we know that the Hartman codes achieves an upper bound of 2 to the n, and that's basically optimal. So for q equals 2, that's good. For general q, the current best upper bound is only slightly sub-exponential in n, whereas the current best lower bound is only slightly super linear, especially when q is large. This is very close to linear. So there's a huge gap between the current best upper and lower bounds. And by the way, all the lower bounds here, they all can be viewed as a lower bound for install LDCs. This is simply because install errors are more difficult to handle. So for install LDCs, here's another table, and the new results that we prove are highlighted in red. So in the constant query regime, for q equals 2, besides the exponential lower bound inherited from the lower bound for Hamming LDCs, we also show that such codes don't exist if we additionally require the code is linear. And for general q, we also prove an exponential lower bound, so it's exponential in n to the 1 over 2q minus 4. So comparing to the slightly super linear bound here, that's a exponential improvement. In the polylog regime, we also prove the super polynomial lower bound when q is something like log n over 2d log n. Okay, so that's our results. Let's get into the techniques. Well, let's first look at the techniques for proving lower bounds for Hamming LDCs. And here's a key idea in proving such results. It's first proposed by Katz and Trevisan in a paper, in their 2000 paper. So the idea is to replace the error correction property with the smoothness property. So the error correction property is best explained in this diagram. It's basically what motivates and defines locally decodable codes. And then Katz and Trevisan came up with the idea that, well, we can replace the diagram with this one, where we no longer have errors, but here we require that the decoder has a property named smoothness instead. And they argue that this sort of already captures what we really want from an LDC, and is sufficient to prove lower bounds for such smooth codes. So what exactly is this smoothness property? Here's the formal definition from their paper. A decoder DAC is C-smooth if for every code word bit j, the probability that DAC reads j is most C over m. So here, this probability just means DAX makes some query which contains the index j. So that's what DAC reads j means. I want to mention here that the KT smoothness only concerns the marginal probabilities. So if you look at this probability, it's saying that, well, if you look at the random query by DAC, then what's the probability that that query is going to contain J? So that's exactly a marginal probability. But our proof will use a stronger notion which involves the joint distribution of queries. We'll see that later. So here's a general framework for proving LDC lower bounds. it's going to be a 3-step process. In the first step, we'll prove a hitting lemma, which says that for each message bit I, we have the probability that the decoder for I makes a good hit for I is at least some constant that depends on epsilon. We call epsilon corresponds to the success rate of the decoder. So here, a good hit, intuitively, it means that it's a query, and the query basically contains a non-trivial amount of information about the ith message bit, xi. Okay, and then in the second step, um, one can show that the good hits are spread out. And this step is possible because of the smoothness property. So for example, one can show that for each I, there exists omega m pairwise disjoint good hits for I. So you can also think of it as a hypergraph matching. You can rephrase it as there exists hypergraph matching of cardinality omega m. So that's kind of saying the good hits are spread out. In the third step, usually that's going to be a combinatorial argument which finally produces the lower bound. And for this step, different papers have different arguments, and we'll take the argument from Katz and Trevison as an example. They showed that for each I, if we take a random set S of size t, then the probability that S contains a good hit for I is at least 3/4. And we can actually take t to be something like m to the 1 minus 1 over q. This is what allows them to prove the slightly superlinear lower bound. For Insta LDCs, our proof goes as follows. The first step is still going to be a hitting lemma, exactly the same as before. And in the second step, we'll prove something we call the good distance lemma. And we can do this because of the strong smoothness property. So the KT smoothness is not going to be sufficient here. For simplicity, let's just assume the Q equals 2, so we only make 2 queries. The good distance lemma says that for each I, there's some parameter j, which we'll call it the distance parameter, such that the following thing happens. So if we look at all pairs k1, k2, such that the difference between k1 and k2 is between 10 to the j and 10 to the j plus 1, then a constant fraction of all such pairs should be good hits for I. So for each I, there is some good distance parameter j for I. And the final step also consists of combinatorial arguments. We proved something like each q tuple is a good hit for big O of q message bits, and therefore each j is a good distance for big O of q over epsilon message bits, and therefore since there are at most log m distance parameters, there can be at most log m message bits. And so this is what allows us to prove the exponential lower bound. Okay, let's summarize. We proved that constant query install LDCs require exponential length. We also proved that constant query linear install LDCs don't exist. Oops. And we listed some open problems. Do we have any constructions? Do constant query install LDCs even exist? And can nonlinearity indeed help? What about relaxations? For example, superconstant alphabet, relaxed install LDCs, and so on. Thanks for your attention, and the full version of the paper can be found at this link. Thank you.